Hi, everybody. My name is David Ross, and I am a physician from Midlothian, Virginia. And I'm here today to tell you about how I broke Newton's cradle. And most of you are familiar with the little toy that kids play with or we learn about in school with five balls hanging from strings, and you let one ball go and another one pops out on the other side, etc. And I'll show you one in just a minute. But I remember in grade school, the teacher showed me one ball, dropped it, and one popped out on the other side. Then she asked me, what will happen if I drop two balls? And I had never seen what happened before when you do that. And I thought, and I was not sure if two balls would pop out or one ball would pop out even faster than the rate at which these two dropped. So I guessed that one ball would pop out, and sure enough, two popped out. If you've ever played with this Newton's cradle, you'll know that. But I actually thought about that for quite a while. Teacher told me, well, two are going to pop out because you dropped two down. And I thought maybe it's not that simple. So I had the theory that there's a way to rig it so that one ball would pop out on the other side if you drop two balls. And so I did an experiment. I'm going to show you that now. And before I did this experiment, I actually looked it up on ChatGPT and Grok and asked it that question: if I fuse two balls, let them drop, would one or two balls pop out on the other side? And both of them told me independently two balls would pop out on the other side, and they gave me a lot of physics equations about kinetic energy and all that stuff explaining why. Then I asked it, has there ever been a video anywhere on the internet or on YouTube that's tried that simple experiment? And both of them said no, they couldn't find a link. So maybe that's out there, but ChatGPT, Grok, and I couldn't find the link, so I decided to make this video myself and do the experiment myself. So let's see what happens when we do that. So now I have fused together the first two balls on the left, and when I pull it up and hit the other balls, we want to see if one or two balls will come out on the right side. And we saw the main effect was that one ball came out on the right side. So what we saw from the experiment was that when we dropped two fused balls, one ball popped out on the other side, and I can tell you that it popped out with equal force to the two balls. So with Newton's law that says for every action there is an equal and opposite reaction, that doesn't necessarily mean when you drop two balls, two will pop out on the other side. It means when you drop a weight here that has a given force, there'll be an equal force coming out with the weight on the other side. So why does this occur? Why do two balls unfused make two balls pop out on the other side, but two balls fused make one pop out? And I think there may be several explanations for that. In summary, these are not perfect systems. And my hypothesis would be that if you had perfect ideal conditions and you dropped two balls that stayed perfectly together the whole time, that you would see only one pop out on the other side. Now that could be tested with better techniques than what I was able to use today with basically a kid's toy. But I can give you a couple examples that I can think of why we have this difference between two regular balls and two fused balls. One of them has to do with slight fluctuations in, let's say, my hand when I'm holding, pretend these are the little steel balls. These are bigger, so they're easier to see. When I pull them back, I might have slight tremor in my hands. In fact, as a physician, I can tell you, everyone has a tremor. You might not be able to see it. It's normal, and it's called normal physiological tremor. But if you measure it very, very carefully, everyone has at least a little bit of a tremor. And if we were to amplify that and I pull them back and my hand's kind of going like this, you might see the balls doing this a little bit. So that when they hit, they're not both tightly connected, but they're both slightly off. So this one will hit first, and then this one hits right behind it. And it happens so fast, you think they both hit at the time when they really didn't. And because they don't hit at the same time, when the first one hits, one ball pops out on the other side. And then when the second one hits right after, a second ball pops out right after on the other side. So it gives us the illusion that the two balls make one impact and causing the other two to pop out, but really it's two impacts in very rapid succession. And if you measured it with a very fast camera rate, you could see the difference in space. There's going to be a little separation between the two balls and in time. And it might be, a millisecond, a couple milliseconds of time, or a very small fraction of a millimeter of distance. Another possibility that also would end up with the two balls not hitting at exactly the same time would be the fact that the way the cradle is designed, remember, the strings come straight down like that. Okay, so here I've put a couple pins on the top of these balls to make it easier to demonstrate. Imagine they're hanging straight down, and the two supports are going straight up. But because they both go straight up, as you pull them way to the side, they're going to start pointing like this. And the point that connects here is different. And so as these drop down, like let's go like that. Like they could be almost, if you hold them way up high, they're going to be almost like this. As you drop them down, they're shifting position till you get to the bottom when they're just like this. And as you notice, this ball is scraping against this one as it comes down. That's friction. That's a force. And what happens when you have friction between two bodies like that? And let me show you that. Okay, so I just showed how as the balls drop, they're rubbing against each other. And then I asked what happens when you rub two balls against each other. And you'd see something like this. Notice how that one on the left moved a little bit away from the one on the right. That's what happens when you have contact between the two. One will be pushed away from the other one. And that leads to a separation, which means this ball will hit first and that one will hit right after. So, could you design a Newton's cradle that worked so perfectly that you drop two balls here and one pops out on the other side? And as I mentioned earlier, I think theoretically that is what would happen, but in the real world, I'm not sure if you could achieve that. It would take my physics and engineering colleagues to try to figure out whether and how you could do that. But a couple ideas that might allow us to do that or get close to it would be, one, instead of having the tiny little balls that are subject to my little bit of hand tremor when I lift them and drop them, you could add heavier balls like bowling balls, and I've seen videos of that. You could also do it in a vacuum so you don't have the air friction that can also jiggle things around and separate the two balls. You could also change the design of the Newton's cradle so that instead of all the support lines hanging straight down in parallel from a horizontal bar, you have them hanging down from a central focal point so that all the balls are on the arc of a circle. And that way, instead of having that movement we talked about originally where they're rubbing against each other, they'd both be in the same arc. So they'd be pointing at the same center of a circle, and they'd be both moving together without the rubbing that you get with the horizontal support. So those are just a few ideas of how you might be able to try to do that without having to fuse the two balls together. So that's how I broke Newton's cradle, and I hope you found this interesting and educational.